Yeah, so like I said, we'll be covering lots of performance related. This is going to include agent performance, yeah, obviously inference performance. And I do have a quick just sort of overview here, the different chapters, talking about sort of what this AI systems performance engineer role is. We go into super deep into the system hardware, talk about networking, talk about, liquid cooling versus air cooling, all this stuff. Really what I realized with this book is this field is so massive, and I'm covering things that are very different than what Chaim is going to be covering potentially today. So, just kind of gives you an idea of the breadth here. I do have a chapter on OS tuning and Docker and Kubernetes tuning specific to GPUs, the Nvidia GPUs. We spend quite a lot of time, or I spend quite a lot of time in the book talking about distributed communication and IO storage optimizations. These are all extremely important, especially for model training, efficient pipelines. I know, Chaim, you've done, I think even like one of your most recent posts was on some of that stuff. So be hopefully pulling in some of that knowledge. And then also talking about, really chapters 5, 6, and 7 are CUDA focused, but I'm trying to not scare people with too much CUDA. And as I'll talk about later for my talk, the NVIDIA GTC conference, which was last month, actually, one of the themes there was more Python support for CUDA. So basically lowering the bar so that people don't have to, sift through a bunch of obscure C++ code, but they will understand how to code for the GPU using Python. So, a lot of cool tricks. There's been some new hardware updates that I'll talk about. That it's good to know CUDA, but really this book is about explaining the patterns for systems optimization and the ability to look at a workload even from a black box standpoint, and look at what the GPU is doing, how it's interacting with CPU and CPU memory and the GPU memory, and so yeah, I think it's going to be a really fun book to read. And then chapters 9 and 10, 9 is dedicated to systems performance for distributed training with large models at what's now being called ultra scale. So these are the 1 trillion parameter models. I even go as far as a hypothetical 100 trillion parameter model and what would need to be done to train that. So that's really cool. Chapter 10, yes, inference, of course, is all the rage these days with, like inference time compute and, reasoning models and chain of thought, advanced chains of thought. And so spend a lot of time in, chapter 10 talking about the different like decoding strategies and batching and scheduling and of course, quantization, these things are all sort of, well understood at this point. But I talk about how to profile, how to do what's called the roofline analysis on these things to see which part of your workload is compute bound and which part is memory bound. The whole book really is focused on transformer-based models. Those are the most popular today, the most heavily optimized, most heavily documented, well documented, thanks to folks like Chaim. And then chapter 11 is about case studies. So these are, real world case studies, people that, have like documented work logs and how they've fixed performance issues. So that's a really fun chapter. Chapter 12 is kind of a speculative future trends in these ultra scale systems and what the AI systems performance engineer is going to look like going forward. Chapter 12 is really cool. We cover the sort of AI assisted, co-pilot optimizer. So, just like the trend is today where we're using AI assistants to write, to like help us write code, we are now able to start using these assistants to look at our, system metrics, to look at our, profiles for the end-to-end, memory usage and GPU utilization, and have it actually find bottlenecks for us and point us to code that needs fixing. So that's really cool. The 13th chapter, I've like never done a chapter 13. 13's been my lucky number throughout life, so I figured I would throw it in there. We have 250 tips for an AI systems performance engineer. And so this is just real quick hits, boom, 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 boom. Really covers like, yeah, pretty much everything in the book in a real bite-sized manner. So there's a lot of content. My guess is this book will be closer to 500. I had originally spec'd it at 300. I think it's going to end up coming in at 500 just because the space is so massive. Okay, and then Chaim, let's turn it over to you. You're going to be talking about AI model performance optimizations for beginners. So go ahead.
Okay, thank you. Let me start by figuring out how to share my slide deck.
Let
Allow
me,
multiple, allow, okay, hold on.
let me unshare.
I think it is this one. Um, and just confirm that you guys can see, I think I'm showing you the notes.
We can see the notes and the little side
All right,
thing
well, I
and
don't want you guys to see the notes. Let me see how I fix that. Um, Maybe I should first put it in presenter mode and then do the share.
yeah, and just to answer real quick, Dynamo is front and center. In fact, the reason I didn't push this book out sooner was because I was waiting for GTC 2025 last month. And right after that, I had to change a whole bunch of stuff because, so yes, the new Nvidia Dynamo like inference server will be front and center. And I have de-emphasized Triton. So that'll definitely be in there. DeepSeek, I cover all over the place within the book as well too, because there's a lot of really good optimizations that came out of that effort. So yeah, great questions. And yeah, Chaim, we could see your slides perfectly.
All right.
Kick it off.
My only issue is that I need to see my notes too. Do you guys still see my slide deck?
We do not. We see you.
Okay. Okay, just give me a minute to sort this out.
Anyone has any other requests? Yeah, PyTorch, I actually have an entire chapter. That's why there's actually 13 chapters because as I was writing, I had PyTorch throughout the book and then realized there's so much, PyTorch, um, the PyTorch compiler, PyTorch, the XLA, a lot of, PyTorch. So basically pulled out a completely separate chapter for that. If you have any other requests, just let me know. Throw them in here.
All right, I'm
Oh
almost
yeah,
there. 1 second.
VLLM is absolutely in there. In fact, VLLM is
Uh-huh.
going to be covered with Dynamo. That'll
Mm.
be the primary backend.
I need to switch displays here. Okay, let's see if this works. No, that's not what I want. 1 more second. Sorry about this.
Yes, I meant to send you the invite for 15 minutes before, and I realized I did it at the top of the hour by accident. So
All right. I think that I can manage like this. Let me just do the sharing again.
also, folks in the chat, can you make sure that you do the drop down so that you're chatting
Okay.
with the whole group?
All right.
So
I think I am ready. Are you
go ahead,
guys
bud.
ready?
We're ready.
All right. Hello, everyone. And thank you, Chris, for inviting me to speak. And I wish you much luck with the upcoming book. It looks very exciting. The topic of my talk today will be PyTorch model performance analysis and optimization. This is a topic that I actually feel quite passionate about. And I would like in this talk to try to convey to you why I believe it to be so important. Okay, now I just got to figure out how. All right, there we go. So first, a few words about myself. I have been working as a software developer for about 20 years in the field of AI, machine learning, and computer vision for roughly the past 12. My specific areas of interest are in cloud-based ML and in ML model performance optimization. In fact, much of my time I actually work on optimizing cloud-based machine learning workloads, as running in the cloud presents all kinds of unique and exciting optimization challenges. I enjoy blogging about the optimization work that I do, and I have including links here to my TDS and Medium pages, where you will find somewhere on the order of 70 to 80 posts on the topic of AI ML optimization. Most of what we discussed today can be found in more detail in my posts. In fact, I'd like you to view this presentation as a primer or an invitation to my blog page, as we will really only touch the surface in this short talk. We're going to start with the motivation behind ML model optimization and review what a typical training step looks like. We'll then discuss some optimization methodologies and walk through a few basic optimization examples. Motivating the need for performance analysis and optimization of AI models is a no-brainer. Simply put, running AI models can be freaking expensive, and training them can take a really long time. In particular, the accelerators used to train AI models, such as Nvidia H100 GPUs, are really expensive and must be used carefully and efficiently, as I find to be wonderfully demonstrated in this image I found online, where this poor fellow ended up homeless because he forgot to shut down an expensive cloud instance. To make matters worse, ML workloads tend to be complex and are highly prone to performance bottlenecks and system underutilization. Fortunately, there are many simple techniques that can deliver significant results, some of which we will touch on in this talk. The main messages I would like to deliver here are: one, the view that I feel very strongly about, that all ML developers must take responsibility for the runtime performance of their workloads. And two, that you do not need to be a CUDA expert to analyze and optimize your model. These are the messages I want to convey to you in this talk, and these are the messages that I try to deliver in my blog posts. I should note that, as it turns out, convincing developers that model optimization is critically important tends to be a lot easier than convincing the same developers to take responsibility for the performance of their workloads. This slide shows a typical training step and explains why AI model performance optimization can be complicated. A typical training step requires streaming data from storage to CPU, pre-processing the training data on the CPU and preparing it for the GPU, copying the training data from the CPU to the GPU, running a forward and backward pass on the GPU, communication of gradients and/or other data across multiple GPUs, passing information back to the CPU, which is often processed and sometimes saved back to storage. There are a lot of components here, each one of which can create a performance bottleneck and result in reducing the training throughput, and also result in resource underutilization. So now that I've convinced you of the critical importance of model optimization, let's talk about how this can be done. Our objective is clear. We want our model execution to run as quickly as possible. To do this, we use performance profilers to measure resource utilization and identify bottlenecks. And most importantly, we need to integrate the analysis and optimization into our model development cycle, as we depict here in 3 steps. Profile the model, optimize the model based on the results of the profiling analysis, and repeat until we feel that we have addressed all of the optimization opportunities. My personal profiler of choice is PyTorch Profiler. Built into the PyTorch library, it is both relatively easy to use, but also extremely useful at identifying bottlenecks, idle resources, and other optimization opportunities. We will demonstrate the profiler output using TensorBoard. but it should be noted that the TensorBoard visualization option was recently deprecated. I've copied a snippet of code demonstrating the use of PyTorch Profiler, but please refer to the official documentation for this. When you open a profile trace in TensorBoard, you'll be taken to the summary view with general details and runtime statistics. The first thing that I always look at is the GPU utilization, which in this case is a very unimpressive 40%. Naturally, the target utilization greatly depends on the model at hand, but I generally like to challenge teams to reach at least 80, even 90% utilization. Of course, exceptions apply. The memory view summarizes memory utilization. In this case, we're using less than 1 gigabyte of memory, which means that we could increase the batch size significantly. The trace viewer, the most important artifact of the PyTorch profile, shows a timeline of the CPU and GPU activity. It is admittedly a little intimidating at first, but once you get the hang of it, you will find it holds a treasure of important information. Here I have highlighted the row that displays fluctuations in the GPU utilization throughout the training step. In the next few slides, I'm going to run through a few simple optimizations, tips, tricks, and techniques, or TTTs. Once again, I encourage you to refer back to my blog posts for more detailed explanations and demonstrations. Let's start with a simple one. TTT1. Parallelize the CPU and GPU activities. For better or worse, by default, PyTorch runs the data pre-processing pipeline and the GPU training step sequentially. This often leads to GPU starvation, where the GPU remains idle as it waits to be fed by the CPU. The fix for this is simple. Use multi-worker data loaders by setting the num worker parameter to a non-zero value. This allows the CPU to prepare the next batch while the GPU is running the training step. The recommended value for num workers is the number of CPU cores, but this should be tuned for optimal performance. TTT2. Choose an instance type that best suits your workload. Many developers tend to blindly opt for the newest, the largest, and most expensive instance type, but this can lead to significant waste. A healthier approach is to familiarize yourself with the many instance type options and choose the one that best suits the properties of your workload. For example, I have encountered developers that were so eager to try out the H100s when they first came out that they chose to use an Amazon EC2 P5 instance with 8 H100 GPUs, even though they were only using one GPU. This is probably the most extreme example of wastefulness that I have encountered. If your workload requires heavy data processing, you may want to choose an instance type with a higher CPU to GPU compute ratio. Your workload may be suited for an AI-specific ASIC, such as a Google Cloud TPU or an AWS Trainium. Or you may require an instance type with direct GPU to GPU links. Moving on to TTT3, minimizing the host-to-device sync events. Ideally, we want to maximize asynchrony and minimize dependence between the CPU and GPU, as synchronization events, such as the one highlighted in this trace, generally lead to dips in GPU utilization. Sometimes removing a sync event is super easy, as depicted here, where instead of creating a tensor on the CPU and copying it to the GPU, which requires a sync event, we can create the tensor directly on the GPU. TTT4, get to know torch.compile. Introduced in PyTorch 2.0, torch.compile converts your model into an optimized computation graph using mechanisms such as kernel fusion and out-of-order execution. This is contrary to PyTorch's default eager execution mode that executes your model line by line. Torch.compile is an extremely powerful optimization technique, and it continues to evolve and improve with each PyTorch release. TTT5, use automatic mixed precision. Using lower precision floating point types can significantly optimize GPU utilization by both reducing memory usage, allowing for increasing the batch size, and by utilizing Tensor Core engines that are programmed specifically for lower precision floats. Importantly, reducing the bit precision can impact model output quality. You can apply PyTorch automatic mixed precision strategies in order to mitigate the potential impact. But in any case, be sure to evaluate the impact on your specific workload before full adoption. Finally, TTT6. Use optimized model components. Take advantage of optimized model components wherever possible. For example, as transformer-based architectures increase in popularity, it is important to take advantage of optimized attention layer solutions such as flash attention, memory-efficient attention, flex attention, and more. You can find more on this topic in these two blog posts. To summarize, here are the key messages I want to leave you with. It is incumbent upon AI ML developers to take responsibility for the runtime performance of their models. Specifically, profiling analysis and optimization should be integrated into every AI ML development workflow. And importantly, you do not need to be a CUDA expert to boost runtime performance and reduce AI ML costs. Thank you for your attention. That was my spiel.
Awesome spiel. We got some really good questions.
Shoot.
A high level question for you, Chaim, is what do you always use PyTorch compile?
Do I always use torch.compile? I do not
Yeah.
always use torch.compile. The reason I do not always use torch.compile is because some models do not perform as well when you perform graph compilation. A very good example of that is models where the tensor shapes are dynamic. When the tensor shapes are dynamic, running torch.compile will cause recompilations uh, depending on what the exact uh, nature of the dynamic nature is, will cause recompiles, recompilations. And recompilations, will after a while, the torch.compile limits the number of compilations that are enabled, but it'll also can significantly slow down the throughput, the training throughput. So torch.compile is not always a solution. However, something that we often do is even in models where you do have some dynamicism. I'm not sure if dynamicism is actually an English word, um, but even in models where you do have these changing tensor shapes, that may not apply to the entire model. So for example, frequently we'll have a transformer architecture that includes an encoder and a decoder, where the encoder is made up of fixed tensor sizes, and the decoder will include this, dynamic shapes. And so we'll apply torch.compile only to the encoder. So the point I'm trying to make is that even when torch.compile may not necessarily apply to the full PyTorch model, often you will be able to apply it to pieces of the model. And even in those cases, the performance boost can be significant.
So things that you would be looking for if this is a relative, black box, let's say, and you're just looking at the logs. If you see lots of these recompiles happening, that's an indicator, right? It'll
Yeah.
tell you when it, yeah, when
Yeah.
it recompiles. Okay.
So it's interesting. So yeah. So you'll basically fail out. You'll see two things. One is that you'll see that your model is taking a really long time to train. The second thing that you'll see is eventually, inevitably, you'll end up getting an error message saying that you capped out on compilations. Um, Now, I will say, and this is one idea I actually have for a future post. I will keep you updated. There are some elements of working with torch.compile that are a little tricky. Sometimes torch.compile will fail, and it'll be a little bit difficult to decipher why it's failing. Um, and so I thought it would be useful to put together a blog post that actually addresses some of these complexities. Even though I do see that it's continues to improve from PyTorch version to PyTorch version.
Gotcha. The GPU mode YouTube channel. Yes. Are you familiar with that? Like
I'm
used to be
sorry that.
called it like used to be called CUDA mode was the name of the YouTube channel. It's some folks out of Meta. Yeah, anyway, like this weekend they did a whole spiel on Torch Compile with someone from Meta and like talked about, quite a lot of this. There still seems to be a bunch of rough edges and a bunch of,
Right.
cases that are not covered, but it's interesting to kind of watch this project evolve over the last year or so. Yeah, I could put a link in here to the so they changed it from like CUDA mode to GPU mode to be a little bit more inclusive for the AMD um, group. So okay, let me get into some of these questions here. Just a couple, nothing too crazy. But
Sure.
yes, please ask questions because we got Chaim here and he's got a lot of experience. All right. I guess some folks are asking, is it the same for inference as training? Like
Yeah,
when
so
does,
so
yeah,
the
go ahead.
answer. Okay, so yeah, so you may have noticed that some of my slides referenced training. Specifically training workloads. But the same tools and the same TTTs, tips, tricks, and techniques, apply to inference as well. And I associate the same importance with, as I mentioned in my key message, with profiling and analyzing inference workloads as I do with training workloads. The truth is that in preparation for this talk, I tried to take out as many references to the training as possible, because like I just said, these important points apply just as much to inference. But I guess some of them still are still there.
Gotcha. How do you profile generative AI models specifically? So someone's saying, I've done this for BERT, but now for, the autoregressive GPT models, the dumped profile becomes around 1 gig for, small
Okay,
payloads.
so generally speaking, when you have those kinds of situations, what I do is very simply I reduce the number of steps for which I profile. So if for a small model, I may have been accustomed to profiling for a duration of 20 to 30 steps. So for a large model, I'll cut that down to even 2 or 3 steps. Um, I have yet to encounter a model so large that I was not able to analyze it in this manner. Um, though I can imagine that if that kind of challenge would present itself, I may go ahead and just cut the model down in size and profile different parts of it piece by piece. But I can't really talk to that because I have not really experienced that firsthand.
And I guess the intuition there is there is going to be a bunch of extra stuff that sort of happens the first few steps while things are, warming up and caches are being loaded and things like that. But then once you actually reach the steady state, that's kind of where you want to profile,
Right,
or do
right.
you
So
want to?
I mean, I have I have my own magic setting where I'll like set the warm up to maybe 10 steps and then profile for 3. Um, but everybody's got to have their own magic numbers.
Sure. And the important thing here is, like you said on your slide, is to, do some profiling, look at the results, make some changes, iterate, and just kind of keep
And
that.
that's right.
that
Keep that up until, there is at some point the law of diminishing returns will come into play. And that's generally when you can perhaps ease up a bit. Um, but personally, I enjoy these kinds of challenges, so I will often maybe stretch it out a bit more than I would recommend other people do. But that's as you said, yes.
Is your workflow, I mean, do you like dedicate massive amount of time, like blocks of time to do this? Because I imagine there's a lot of complexity and a lot of different dimensions that you're trying to analyze. And like, what does a typical sort of profiling, debugging, iterating stuff
Oh,
look like?
okay. So yeah, so first of all, that depends a great deal on the actual model. Um, and yeah, a lot of this comes with experience, right? So it could be that the first or second amount, and the trace view that I showed that holds this wealth of knowledge is as I mentioned in the slide deck is intimidating, and I remember the first two or three models that I myself would analyze, feeling quite intimidated by it. Um, but as you gain experience and as you see more models and more and different types of ML workloads, you start to get the hang of it. I think that I do want to emphasize I don't consider myself a CUDA expert. In other words, I feel like I'm really practicing what I preach. Um, I don't consider myself a CUDA expert. When I do come across some really tricky issues, I will sometimes consult with, Nvidia specialists or, you know, seek out a CUDA expert. There aren't that many of them, as it turns out.
Yeah.
Um, uh,
Where do you do that? Do you do that on the PyTorch discussions and hope someone
oh,
responds
I
monitoring?
have my contacts at Nvidia who
Okay.
shall remain unnamed.
Remain nameless. Yeah. Yeah. They'll get pounded with questions otherwise. Yeah.
Yeah,
That's one thing I've noticed about NVIDIA. They don't do a lot of like speaking, you know, like on the side. Yeah, all the messaging is very, centralized
right.
and
But this is not common. I mean, the last time that I spoke to him was many months ago, right? Most of the stuff that I do is really, you know, b- based on just what's online, and using the basic API offerings. Um, it's rare that it gets to that point.
do you okay, and I guess the primary channels I've used anyway are the PyTorch discussion lists, the NVIDIA forums I've had mixed success with. I don't know who's actually
Right.
paying attention to those over there, but hopefully, someone's watching those. Yeah, any other tips? Is it just Stack Overflow or you just have to make
I would
connections?
highly recommend my blog post.
Yeah, yeah, for sure. Yeah, and I was saying this in the beginning for those that joined late, but as I've been researching for my book and figuring out what topics to include and not include, I keep ending up on Chaim's blog. So, and I've posted the links many times here. Um, so another quick question. Where to go? I'm interested to understand the phases to run the profiler, which gives the most useful data. So start of the model, in the middle, and at the end, what works best?
So I actually I think it would be a good idea to actually just look at the official tutorials on the PyTorch documentation. I think that they're pretty good. I don't think that any answer I would give here would would do it justice. So I would highly recommend just opening one of the tutorials and following the pretty detailed instructions there. Um,
Is that the tuning guide that you were talking
So they're
about?
actually no, it's not the tuning guide. There's actually, if I recall correctly, there are two tutorials. One demonstrates the profiler API. These are both in the PyTorch documentation. And the second one that I actually find to be even more useful is the one that demonstrates not just how to set up PyTorch Profiler, but also how to visualize the outputs in TensorBoard. Um, that I think is that's the tutorial I actually would recommend um,
Okay.
personally.
I see a profiler recipe.
Yeah, you want me? I can find the real fast the link to that
And
PyTorch.
out of curiosity, do you
So
ever
it's called.
use?
I'm sorry. Let me
Yeah.
just tell you what the link is. It's called PyTorch Profiler with TensorBoard. I'll paste the link in right here. Oop. I will try to paste the link in right here, but my screen froze.
I think I found it.
Here we go. Oh,
Yeah. That other one was the profiler recipe, and then this. Okay, so yeah, profiler tutorial. Okay. Now I saw something in your slides that said TensorBoard is actually deprecated. When did that happen?
yes, yes.
That's
So no,
huge.
okay. So I want to be. Let me just clarify. My understanding is that TensorBoard is deprecated for this specific usage. TensorBoard is not deprecated, but for the purpose
Oh,
of visualizing the output of PyTorch Profiler, it's deprecated. That's my understanding, at least. The PyTorch is sometimes kind of surprising when it comes to just like separate uh, deprecating popular tools. Like I saw 2 weeks ago that they're deprecating uh, uh, the PyTorch inference, Torch inference server, Torch serve. That's now entered maintenance mode, and I was shocked because that's, as far as I can tell, a very very popular tool.
hmm.
Um, so yeah, so TensorBoard is deprecated for this specific usage. On the webpage there, they actually recommend two other tools. To be honest, I really like TensorBoard, so for this specific use, so I'm still using TensorBoard even though it's been declared
Hmm.
deprecated, and I have on my to-do list to find a satisfactory alternative.
Yeah, that was going to be my next question. Have you tried using NSYS, right? Like the NVIDIA
Okay,
Insight
so yeah,
Systems Compute?
I do have some experience with that, and I'll tell you my own personal experience. So my own personal experience is that it's a lot harder. Uh, the convenience of having this profiling mechanism built into PyTorch,
Mhm.
you can't underestimate that. That's a real, I can't overstate that. That's a real plus. Using the NVIDIA tools, um, not specifically the NSYS, but their whole suite, it's a pain in the neck. And I hope there are no NVIDIA guys on this call. Or you know what? I actually hope that there are NVIDIA people on
Actually,
this
hope,
call.
yeah.
Yeah, it's a pain in the neck. I mean, this may have gotten better since the last time I tried, but the setup, just the setup required is really complicated, and I have not, and I actually searched. I actively
Yeah.
searched for uh, things that the added value of using the NVIDIA profiling tools over the PyTorch profiler, and it's hard. I mean, there were some specific ones. This is one of the times where I did speak to an NVIDIA specialist to
Mhm.
try and really pinpoint what do I need it for? Why not just stick with the
Mhm.
PyTorch profiler? And we were able to come up with a few, but not they weren't as strong enough arguments for me to deal with that, go through that headache again. So
Yeah.
for any NVIDIA folks on the call, you guys please uh, clean that up. Um, and if you already have, then I take that back.
I heard some rumblings when I was at GTC here in San Jose that they're considering, uh, yeah, all of these issues, and potentially, hopefully, by next GTC, there might be something that makes it a little better. But they do recognize that a lot of folks are kind of in this weird, like for PyTorch specifically, they're in this weird state. Now, one thing that they just did announce is Insight Systems now can do Python call stack traces, which
Right. I read
includes,
about that announcement.
yeah,
Um, I mean, I don't know. I haven't tried it out myself, so I can't.
yeah, yeah, yeah. It looks pretty good. I've been using it for the book. You know, I guess between me, you, and the hundreds of people on here, I feel like I'm nervous that they're going to deprecate that PyTorch profile or somehow change it. I mean, I don't think they
Right.
can because a lot of folks use it, but who knows, right?
Um, from your mouth to whoever's ears.
How about NVProf or
Same
um,
thing. That
yeah,
that to me, I basically combine them all together.
yep.
Um,
Do you have any experience, or sorry, are you setting up like benchmarks as part of your CI/CD build system? Like, are you actually running
ru-
benchmarks with every?
oh, all the time.
Yeah.
All the time. That's a part of the the profiling analysis optimization repeat thing is it includes actually introducing timing mechanisms, measuring the step time, um, calculating the throughput, the samples per second. I actually use a different metric, not samples per second, but rather samples per dollar, uh,
Oh,
which
there you go.
takes into account accounts for the opportunities to train and different instance types that may have different associated costs.
Yeah,
Um,
yeah. Interesting. Um, let's see. I think there was one more question I wanted to. So the cost, yeah, the cost is really interesting. I was surprised when I work with customers that they don't do that more. I think folks have an instance type, they just
yeah,
stick to it, and it's
it's sometimes astonishes me. It's
uh
astonishing. There's no better word for it.
yeah, yeah,
Um,
yeah.
because I hesitate saying this too often because oftentimes when I will say this, I'll suddenly have a harder time accessing these cloud resources. But I love the L4s, L40s, A10s, A40s, all those small GPUs. I find them to be extremely price performant. Um, uh, for training too. That's maybe I should have emphasized that. Even for training, even though these instance types are more often um, targeted for inference use cases, I find them extremely price performant at training as well. Um, but don't tell too many people. So, because I don't, I want to be able to get those instances when I need them.
Hilarious. Um, have you tried the new Blackwell, the new
No,
or
I have not.
Grace Blackwell? Okay. Yeah, um, I can get the H100s pretty easily now for relatively cheap off or on these marketplaces and things. But
Right.
um,
Relatively is the key word there.
yeah, gotcha. Okay, I think. I'm gonna, let's see, we have about 10 minutes or about 12 minutes left, so I'm gonna quickly do my stuff. If there's any
Okay.
other questions that you find interesting in the chat, but I think we covered most of them.
Okay.
Um,
Chris, thanks again for the opportunity. I don't
I
really
would
see
love to have
anybody
you
else,
on.
so I have no idea who else. But thank you, everybody. I myself am going to have to drop off. Um,
Awesome.
but
Yeah, thanks for your
I
time.
thank you all.
Yeah, I hope to have you on, many more times because like
Oh,
you're always
I would
doing
love to.
something very interesting.
I would love
Awesome,
to.
but yeah, so let's catch up too offline. So
Take care.
see you, man.
So long.
Okay. I still have some slides here, so let me share my screen and we'll get this going. I have just a quick number of slides here, so it won't go over it. Okay, so I did cover, just quick recap here. So this was Chaim's talk, talked about model performance, really sort of systems performance. I'm now going to talk about some really interesting Nvidia GTC. This is their yearly conference. I've been going to this conference. I've been paying for it myself, even for I think the last, 12 years. It's here in San Jose. It was an absolute craziness this year. There were, I think, 30,000 people, which is getting up there, and those sort of Amazon reInvent type of numbers. Um, and I'm specifically going to talk about highlights that are targeted towards AI systems performance. And this is going to be, hardware. Um, I quickly mentioned the book here, the things that I'm covering. And let's get right into the keynote. So keynote, Jensen Huang's pretty funny guy on stage. He tends to just talk sort of freely and doesn't really stick to any script, which is always fun. Very, very opposite from when I was at like Amazon. All those things are very well scripted. They don't stray too far. Jensen just has bullet points and he just talks and he sometimes says kind of things that are not necessarily, stock market friendly, I guess, but they somehow made it through it this time, although the stock is down a little bit as of this talk. But okay, so the big thing is that the NVIDIA Blackwell is finally in full production. There were some issues going on here. There was a lot of rumors. I actually don't know the details. I read the same things that you folks read, but I think there were some cooling issues and rack issues and data center issues. So all that's been worked out. Um, so it's not just Blackwell GPU, it's also now the Grace CPU, which is an ARM-based CPU combined on the same die, or sorry, on the same silicon as actually two Blackwell GPUs. And all of them share memory space. They have unified memory. They have really fast interconnects. That's called NVLink chip to chip. And so, really cool perform. Now, what's very interesting is that we are no longer now just programming to the GPU, but we also have to keep in mind that the CPU and the GPU actually have a unified shared memory space. Now, there's some performance issues here. I cover them in depth in the book. So if you can use the pure GPU, high bandwidth memory, obviously stick to that. But you do have access to it now, a massive amount of CPU RAM on the order of I think 512 gigs, something like that. Whereas these Blackwell GPUs only have access to I think 192 or something gigs of the what's called HBM, the high bandwidth memory. NVIDIA did reinforce the fact that they are going to release on an annual cycle. They've also given their roadmap for the next few years. Jensen, the CEO, is very proud of the fact that he works with the partners, gives them the 3-year roadmap so that partners know what's coming. There's no surprises. They did announce what's called the Vera Rubin, and that's the equivalent of Grace and Blackwell. So Grace is the CPU, Blackwell is the GPU, Vera is the CPU for 2026 and beyond, and then Rubin is going to be the successor to the Blackwell GPU. And then obviously combining these into what they're calling super chips, by the way, this combination of CPU, GPU on the same silicon. The other big thing was photonics-based networking. So this actually occupied a fair amount of Jensen's his like keynote talk, which is about what they're calling, I believe it's called co-packaged optics. So CPO. I have another slide on it here in a bit, but think of this as really, really high performance photonics based networking. What we are all starting to realize about Nvidia is they're not just a GPU company anymore. And they did reinforce this quite a few times during the whole conference, not just the keynote, but they are a networking company. They're a storage company, they're working with storage partners. There's a heavy focus now on AI optimized storage for massive large scale training, loading large models, for inference and being able to share KV caches, like a lot of details dealing with high performance networking and storage. So basically, as we're scaling beyond a single chip into 8 chips, into 16 chips, into millions of these Grace Blackwell GPU or super chips being networked together. So the goal here is to support 1 trillion, 100 trillion parameter models. The only way to do this is to scale these things out in the data center across racks and within racks as well too, of course. There was also, of course, mention of physical AI is a $50 trillion opportunity. This is a very big number, so kept it in here for the keynote. The products that they have focused on this are called Isaac and then Cosmos, and this is for AI-powered robotics, automation for manufacturing, logistics, healthcare, and other vertical industries. All right. So yeah, once again, Blackwell GPUs in full production. They quote all these crazy numbers 40 times the previous Hopper generation. So it was Ampere, that was the A100, Hopper, the H100, and we have Blackwell, the B200, and then there's going to be the Vera GPU, which will be something like a V200, V300, something like that. They also announced a second half of this year is going to be what's called the Blackwell Ultra GPU, and this is going to have a faster transformer engine, which is obviously optimized for these transformer-based attention models. This is going to deliver more flops, and it's got better more floating point 4, floating point 6, floating point 8 support. They also announced later this year there's going to be the Grace Blackwell 300. Now, so I have not mentioned this yet, but they have this rack scale system called the NVL72. And what this is this is 72 GPUs that are in a single rack, and it's shown here on the right of these Grace Blackwell chips. They have a Grace Blackwell 200. Now they are going to come out with the Grace Blackwell Ultra NVL72. This is a massive beast. This thing can handle 1 trillion parameters within a single rack. You can link up to 8 of these racks and, obviously scale out the size of your models that you're training or support more users for inference. On kind of the personal fun note, they do have this sort of mini DGX called the DGX Spark, and it's shown here on the right, and I'm showing relative to a laptop. So these are, small looking, very small profile. These are supercomputers that you could put on your desk, and you have access. You can actually chain a bunch of these together. Price point, I think, is about 3,500, maybe 4,000. So it's a little bit pricey, but gives you pretty high performance, and you could do this locally without having to provision cloud resources, which can get pretty expensive. So I think they have about 4 terabytes of storage. They have what's called the GB10, I believe, is the Grace Blackwell. So it's a little bit scaled down. It shares memory with the CPU. I think it's got 128 gigs of RAM. It's enough to hold a pretty sizable, Llama model or DeepSeek, 70 billion model. So Vera Rubin, yeah, like I said, and then also the Rubin Ultra will come in 2027. So, Vera Rubin Grace is, Vera is the equivalent to Grace. Rubin is the equivalent to Blackwell next generation. So sort of confirming that there is an annual release cadence. They are, of course, planning a Vera Rubin NVL 72 and potentially NVL 576. That's 576 GPUs that are all inside of a single rack. And then, of course, you could scale out. So more on the networking hardware. So I did mention that the CPU and the GPUs talk to each other with what's called NVLink C to C, chip to chip, and this is a 1.8 terabyte per second like interconnect. It's the 5th generation of this, and you can see kind of a step climb here. So the A100, how fast that 3rd generation NVLink was, up to the 4th generation, up to the 5th generation here, up to the 1.8 terabytes per second. Okay. And then I did mention co-packaged optics. This is called CPO, and this is going to be silicon photonic switches, and with the actual optics on chip. This is a 144 port switch, 800 gigabit per second per port. And what's really cool is that this is the first liquid cooled switch. And so we're not just liquid cooling the racks, but now Nvidia is going to start liquid cooling their photonics to keep these things running. I did mention there is a huge push towards storage. So the Nvidia folks have created this reference design called the AI data platform, and this does integrate their networking NICs that are called Bluefield DPUs or data processing units. Blackwell GPUs, networking, technology called GPU direct storage. If you're familiar with the old Mellanox, so back in 2019, NVIDIA did acquire this company called Mellanox. So I believe this used to be called Mellanox Direct Storage. It's now called GPU Direct Storage. And they're also, interestingly enough, including Dynamo. I think I switched the slides a bit, so I haven't quite mentioned Dynamo yet, but this is the new inference server. So let me talk about that in a sec. But here's some of the partners that are integrating. You've got Weka and Dell and NetApp, IBM, all the typical players, HPE, Pure Storage. Okay, so that's on the hardware side. Let's jump over now to the fun software side. So the new CUDA toolkit does now. So prior to this release, the Python focused CUDA libraries were sort of separate, and they were just kind of maintained outside, maintained by different companies, Anaconda, and maybe some experimental libraries from the NVIDIA folks themselves. They have now rolled in. So CUDA is now no longer just C++. That's really the big takeaway from this. CUDA toolkit actually comes with these Python libraries. They have something called CUDA Python. Here's a bunch of the packages shown in the bottom left there. These really are targeted towards PyTorch. You'll see, lots of PyTorch examples here, but this also does unify the Numba project, which comes out of Anaconda. Puts everything here. They've got, of course, and so as we've sort of always known, Python libraries like NumPy, SciPy are really just wrappers around the C code and, C++ code to make them performant. And Python version of these is just sort of convenience for, Python developers to access the C code without having to worry about, those C details. So similar thing happening here. So there's a whole CUDA Python sort of ecosystem that's now going into the CUDA toolkit. There was a lot of emphasis on this Python library called CUTile, and this is a convention that the like CUDA folks tend to use, which is they prepend CU to some name, and this is CUTile. And one thing that you'll realize pretty quickly, and I focus on this heavily in the book, is that you have to work with tiles of these massive matrices, right? When you're doing matrix multiplies, you can't always, just because of the sort of hardware limitations and trying to co-design your software with the hardware, really it makes sense to break up these matrix multiplies into what are called tiles. Some people call them submatrices. And because of the properties of linear algebra, we can tile these things up process them in chunks, if you will, and then aggregate or reduce the results. Also, Qtile, and this is a Python library that's using C under the covers, does take advantage of tensor cores and pipelining and various optimization techniques for you. These are all things that CUDA developers that at the C++ level have been doing for quite some time, many years now. They know these tricks, and the NVIDIA folks are starting to realize that they need to appeal to the Python folks, and specifically PyTorch is a big focus. Okay, there's also this transformer engine, which is something to pay attention to. This is in the NVIDIA open source project. It does implement and focus on flash attention. And if you're familiar with the transformer model, the attention mechanism, the attention part of that is a very key part. So they've been very, very heavily optimizing it, and they do now support the Blackwell GPU in a first-class manner, and specifically the FP8, and I believe FP4 as well too, but I'm not sure why it's not listed there. Okay, this was probably the most exciting update. This was the one I did not see coming. Up till now, NVIDIA has been pushing what they were calling the Triton inference server, which is extremely confusing because there's a lot of Tritons, and there's an OpenAI project called Triton that is a Python library, or like Python DSL for writing CUDA kernels, and it was just all kinds of confusing. So from now on, never speak of Triton again, unless of course you're using it in production, which it is still supported, enterprise support from NVIDIA. It's not going away. It's just now the focus is on the NVIDIA Dynamo project. And coming from Amazon, Dynamo actually is an overloaded term as well too, but I've been able to get past that, and NVIDIA Dynamo model inference server. So successor to the Triton inference server, and this really has and is performing and sort of orchestrating disaggregated prefill and decode, smart routing, dynamic GPU scheduling, the ability to offload caches. In the bottom right, you can see the caches can either be in GPU memory, host memory, local SSD, and shared network storage. Of course, the smaller, but then at the top are the very fast memory, and then down at the bottom is the slower storage. What was interesting was NVIDIA has been referring to this as the inference operating system, which is sort of an interesting way to look at it, but let's just go with it. It's good enough for me, so I'll stick with it. Backends that this Dynamo model inference server support are your familiar VLLM, TensorRT LLM, and SGLang. So these are now considered backends to the front end model inference server, and so you can plug these in. Something very interesting, if you start to look through the Dynamo source code, which this is an open source project, by the way, I should probably make that clear. Dynamo model inference server is open source. You will see that Dynamo's default backend is actually not their own TensorRT LLM, it's actually VLLM. So, interesting tidbit, if you don't specify anything, it'll automatically use VLLM. And so the book goes very much into VLLM. I'll be covering VLLM in future sessions, try to get some other experts on as well too, to talk about the roadmap from that project. They did make a big deal, the NVIDIA folks made a big deal that they were able to serve a 671 billion, this is the biggest DeepSeek R1. This is a reasoning model. They did set what they are calling the world record for the most tokens per second. Now, this is in aggregate across many users. If you look at an individual user, they were actually getting 253 tokens per second. So that's how many tokens are flying across your screen. 250 is kind of a good number. I think, between 150 and 250 is sort of how the human can actually, that's as fast as the human can actually read. So pretty good number. And this was on a single 8 GPU Blackwell DGX node. One single node was able to serve, with 8 GPUs, was able to serve the 671 billion DeepSeek model. Yes, obviously it was quantized in various ways in order to fit, but pretty good performance overall. Okay, and then I think this is the last slide. There have been some major updates to Insight Compute and the Insight systems. And if you're not familiar with these are kind of the equivalent to the PyTorch profiler that Chaim in the first talk was talking about. They're really real. They're yeah, the folks at like Nvidia, and I spoke to tons of people about this. I actually spent pretty much half the time I was at GTC in a lot of these sessions talking to these engineers and these product managers. They recognize that the most important thing is to get the best performance out of these GPUs. They know that they're expensive, they know that they're really powerful, and they know that folks aren't always able to fully utilize the power of these GPUs. So they've been adding a lot of things to the GUI. They've been adding more, metrics to be monitored, more ways to highlight performance, and to provide suggestions. And so I cover this very heavily in the book. A lot of the speakers I'm going to have on this channel will certainly be covering these parts of it. So Insight Systems, the other thing I mentioned earlier was now supports a Python call stack view. So before, when you would profile, when you use these tools, you had no idea where the code was actually, how to actually get back to the Python source code or the PyTorch source code that was causing these stalls or these excessive synchronizations from the GPU back to the CPU. Now I can actually start at the bottom of this this flame graph, or what's called icicle graph, and I can go up and see where in my code is this actually happening. And this is super useful because now I can get directly to the line of code that's causing the problem. I can reason through it and realize, oh, I'm actually not using the GPU in this case. I think I am, because I'm just writing PyTorch code, but actually this code is running on the CPU, which then, pauses everything, forces the data to get pushed back into the CPU memory, which is a very expensive operation. So yeah, like really cool stuff here. Insight Systems is a way to look at the entire system. Insight Compute is a way to look at a single kernel or a set of kernels and see what's happening inside those kernels. And so there's actually, sort of two levels to look at here. There have been some updates also to the PyTorch profiler that weren't necessarily announced at NVIDIA GTC, but we will be covering those in future sessions. Okay, so let me leave that here, and let me look at questions, see how many I can answer. I know we're over time, 10 minutes over time here. How do I get back to my questions? Okay, let me look at these questions here and see what I can answer. Okay. Gotcha. Let's see. Yeah, the slides, I'm definitely going to post those. I've got a GitHub link here at the bottom, which is right now, it's just my GitHub. So I'll put that in here. And I'm going to post all the presentations. It'll be somewhere in there. I think I've got one called AI Systems Performance Engineering something. Yeah, it'll be obvious once you're in there. Okay, provider and database. The Intel's vTune was $5,000, worth every penny. Okay. Yeah, so the DGX Spark is pretty cool. I was speaking to some folks at GTC where they're actually linking up multiple of these DGX Sparks and then able to simulate multi-node training and inference. Let's see. Also, the other thing to mention about the profilers, which I didn't know until I started using it, is that there is Mac support for the profiler. Now, of course, your Mac does not have an NVIDIA GPU. They did at one point very briefly back in the late 2010s, I think, but went back to a different GPU. But what's cool is you can export the profiling, and in probably the next I think next month I'm going to focus on NCU, which is the Insight Compute, and then Insight Systems, and I'm going to show a whole bunch of different scenarios. These are actually the chapters I'm finishing right now, and show you, how to identify the issues, and then make the change, and then rerun it and see the results. And so, yeah, that'll give you some insight into Insight Compute and Insight Systems. Okay, let's see. So, yeah, so it looks like a bunch of things were discussed here, and I think, yeah, Nvidia picked an ARM-based instead of RISC-V. Pretty interesting. Yeah, workstations. Yeah, the book is on Amazon in pre-sale. There's no preprints right now. We're still working through those. Let's see, and I'll be sharing the slides. So, yeah, thanks so much, everyone, for staying around late. And we will see you the third Monday of every month going forward, just like we did the last 10 years. If you didn't, or you may have realized that we took the last few months off. That was part of this whole retooling, figuring out how we're going to go forward, what we're going to focus on. And after talking with many people and working in this space now for the last few years, performance optimization, realized that there's a lot of knowledge that's floating around Twitter posts and GitHub repos and all kinds of and like YouTube videos, and decided to bring it all into one meetup. So thank you much. If you do, I'm going to put my email in here. Whether that's good or bad, but if you do want to ping me, that's my email, and let me know if you would like to speak on a future session. We would love to have you. We would love to hear your experience, and thank you very much. See you next month, everyone.